Alright, everyone in the crypto space. This is my second take on this video because the first one did not record the audio. So hopefully this works. I think it's working. Anyways, so this is going to be my take at explaining blockchain and cryptocurrencies in terms of what blockchain is and their use cases. So yeah. I know there are videos like this on YouTube, and at this point, if you don't know what blockchain is, you're probably living under a rock. But I figured that, I want some content on my video. I want some content on my channels, so I might as well just make this, and hopefully I can explain things in a way that makes sense and doesn't really complicate things. All right. Let's see. Okay, so here's the outline of this presentation. It's gonna be sort of be like a class, not class, like an academic presentation, but I'll try to explain things in simple terms. So basically, here it is. I'm gonna go over data structures because blockchain it's basically a data structure, but it's used in a different way compared to other ones. I'm gonna explain hashing algorithms because blockchains use hash algorithms, and that word hash and hash rate that gets thrown around all the time. So hopefully I can clear things up what it means. I'm going to demonstrate how blockchain ensures data integrity due to the chaining of hashes and previous hashes. I'm also going to go into a little bit of decentralization and some consensus talk that all that adds utility to blockchain. I'm also going to go into the Byzantine generals problem, how that ties into decentralization, and how it's an analog, or how it's an analogy for all the problems that decentralized systems face. Then I'm going to flow into use cases and how decentralization and blockchain give rise to cryptocurrencies. And then I'm going to wrap up by just going over the outline again in terms of everything I just explained. All right. So yeah, blockchain is just another data structure similar to your linked lists, hash tables, trees, and graphs. And what a data structure is, all it is just a way to organize data in a computer. And there's really not a lot to data structures. They're organized in linear ways or in non-linear ways. So for example, you have a linked list, which is this image down here, the only one that says head and A, B, C, D, and null. So what is that like? So in this case, data is organized in a linear way. So if you can access the first data payload A by accessing the head, and then you can go on to the next data payload B, C, D. It all goes in one direction in this case. In this image, it all goes in one direction, but linked lists can go bidirectional. But that's just one example, really. So that's a linked list, and here you have a hash function. This is not a hash function. It's a hash table. This is just a diagram of what a hash table would look like, and I'll explain later how this all ties together. And here's a tree or a graph, which is basically a tree it's a linked list, but instead of in one direction, you can go in an arbitrary number of directions. And in this case, we have a binary tree where you can go two ways only. See, from one node, you can go two ways for each node, or up to two ways rather. So this one only has one. Okay. All right. So a hash table. So think of it like this. Hash tables are like linked lists in the way that the values that are stored in a linear way. But the only thing that's different from a linked list and a hash table is their lookup time. Now, what does that mean? So lookup time is just how fast does it take to find data in the data structure. So for example, in a linked list, depending on if your list is sorted or not, will influence how fast it is to look up data. So in this case, this is a sorted list because it's the alphabet. So if you wanted to find the letter D, you could use a binary search, and a binary search will it'll search half of the list and do some comparison heuristics and decide whether it should go up or down the list. And that really like reduces the time for searching. But if it's unsorted, if it's an unsorted list, then you have to sort through them one by one. You have to search through it one by one. And if your list is sufficiently long, it'll take your computer a long time to look through an unsorted list. So that can be problematic in terms of performance. Hash tables, on the other hand, they they have this hash function that takes keys or the data you want to store and associates like a one-to-one relationship to a value, which is the data that is going to be associated with the key. And how does that happen? Well, you take the key, you throw it into a hash function, and it produces an index or a number in a list. And that gives you immediate access to the data associated with it. There's no need to like sort through each individual block or look through each individual block to find your data, because all you have to do is give the hash table the key, and then it will spit out the value associated with the key, because the hash function produces a one-to-one relationship. In this case, the hash table produces a single number that is associated with the position in the list. Some hash functions produce like a string of characters that's a one-to-one relationship, but for hash tables, the hash functions are made to produce a single number that's associated with the key in order to produce the value. So yeah, that's the gist of data structures. Basically, they store data, they have a specific lookup speed and space consumption, and they're also different by their ease of implementation. So like it's easy to implement a linked list than it is to implement a tree or a graph than it is to implement a hash table. So yeah, that's just data structures in a nutshell. So blockchain as a data structure, well, it is a linked list type where like each block is connected to one another in a linear way, and they're all associated with one another based off the hash of the previous block. But what makes it different from a linked list? Well, data integrity. Because since we have this chain of previous hashes, we can be sure that the data stored in all the blocks beforehand are not tampered with. So it's tamper resistant, but it's not tamper immune. Because if you were to recalculate all the hashes after you tampered the data in the blockchain, you'd have effectively a completely new blockchain, and nobody would be able to tell if there was a tamper going on. But anyways, I'll go into more detail in terms of that slide. But before I do that, I have to go over what hashing functions are, because you hear this term a lot. You hear hash rate, hash function, hash, or whatever, and it can be kind of nebulous if you don't know what it means. You might be confused and think it's just a hashtag on Twitter, but in this case, what hashing is, it means large to small. What that means is you're mapping lots of data to a small string of data. So let's say you have a book. Let's say you wanted to hash like the Bible or something. There's a lot of like a digital version of the Bible. There's a lot of data in the Bible, obviously, because there's a lot of text. So if you were to hash that, just to like simplify it, you get like some, like, let's say 500 character string of random text. But the thing is, the hashing algorithm or the hash function, that random string of 500 characters is a one-to-one relationship to the Bible you sent in. If you were to change one character in the Bible, like let's say if you were to remove a period somewhere, that 500 character text will not be the same even though you changed one character. That's the thing about hashing functions and hash algorithms. They are one-to-one relationships to, like, they're very specific. You can't just put two things that are close together and hope they'll give you the same hash or hashes that are similar. They'll produce good hashing algorithms will produce completely different hashes for two pieces of data which are somewhat similar. Even by just like a period, they'll produce two completely different hashes. Anyways, that's what hash functions do. They represent large data as short strings of characters in a one-to-one relationship. So yeah, and here's just an image of what hashing algorithms actually look like. This is Python. It's a very basic programming language, and in this case they're using a library to implement hashing. So this is just like a snippet of the algorithm, just to give you an idea, because it's all just computer code at the end of the day. Anyways, now here's an example of tampering with a blockchain. All right, so the way I designed this image is that each block is represented by the blue square, and each hash is represented by a hashtag icon. The block's own hash is right next to its payload or its ledger or its transaction list or whatever you want to call it, its data. I'm going to call it payload. So the payload is right next to the block's own hash, and the previous hash is below the payload. And in this case, in the Genesis block, there's no previous hash, so it's rendered as null, so basically not pointing to anything, no data. And here in block 2, we have its payload, its own hash, so it's blue. So the color indicates a different hash. Like it could be just anything really. I didn't want to write out a string of characters because this would have made this slide look too big. So I'm indicating that different hashes are colored differently. Here we have the white hash, which is the previous block, the Genesis block's hash. All right, so that's how this image works. Now let's say if we wanted to tamper with block 2's payload, what's going to happen? So if we tamper with block 2's payload, its payload is going to be different, and its hash should also change. Now, why is that? We don't know what hash it's going to be because we haven't produced a new hash yet, but this hash is no longer valid because we changed block 2's payload. And the way I was thinking about this is that in order to produce the hash, you need to feed in the payload and the previous hash, basically the contents of the block. And that's what produces the hash of the current block you're at. And since we changed the payload of block 2, their hashes will not match. The hash of block 2 won't match anymore, because before the hash was orange, right? And this orange hash is a one-to-one relationship to this payload and this hash. So block 2's payload and the previous hash. But as soon as we changed block 2's payload, that one-to-one relationship is broken, so we don't know what hash this produces anymore. Okay, so how do we fix this? How do we tamper this blockchain and get away with it? Well, we have to reproduce block 2's hash, otherwise there's going to be some inconsistency between block 3's previous hash and block 2's current hash. So let's say we recalculate the hashes on our computer. Oh, that's good. Now block 2's hash and block 3's previous hash, they match up, they're both purple. Okay, but like I said before, the hashing algorithm takes in the payload and the previous hash. So since we changed the previous hash on block 3, that means the one-to-one relationship between block 3's current hash and what its hash is supposed to be are different. So, I mean, the one-to-one relationship between block 3's data, so its payload and its previous hash, is broken between its current hash. So, like I said, hashes are one-to-one relationships. If we take in the payload and its previous hash and throw it into the hash function, it will produce, for in this example, a green hash, and that'll be 3's valid hash. But if we change anything, the payload, the previous hash, or some metadata associated with the block that goes into the hash as well, that one-to-one relationship is broken. So we can't mess around with that stuff. But unless we recalculate the hash, which is the goal of tampering with blockchains, is where you change the data, recalculate the hashes, and then throw the blockchain out again. So if we do that, we get some brand new hash. Let's say it's a black hash, and the hash and everything checks out, everything works, everything's consistent. So we do that. Oh, and everything works out. Oh, I think I messed up over here. So in my previous 2 slides, I had a purple hash, and here it's red, but I just forgot to change that, but these should be purple. But anyways, we changed, so if we successfully change block 3's hash, okay, that checks out, because if we hash the ledger or the payload and its previous hash, that will produce a black hash. Good. But remember, it's a blockchain, so we have to keep hashing through until we're totally done. Block 4 needs to be redone here because its previous hash doesn't match with block 3's hash. So we change that. That's all good. But now its own hash is corrupted, and we have to recalculate its hash again. So I hope you can see how this ensures data integrity on the blockchain. It's because of it's these links of previous hashes which ensures data integrity. Now this is all easy to do. Back in 1990s when blockchain was invented, it was really hard to calculate hashes because computers were really slow. But nowadays, it's really easy to rehash a blockchain that is stored on a single computer. You could probably do it yourself if you were to download some blockchain library and just create a blockchain on your computer. You can tamper with the blockchain yourself. So what's the point of blockchain then? Well, it's easy to do on one computer, but imagine if the blockchain was stored across hundreds of computers, thousands of computers. What then? Okay, in that case, then blockchain is pretty useful because the payload, the chain itself, is decentralized. So decentralization is what makes blockchain useful, and it's what adds to its utility. So yeah, it'd be really difficult to just hack all these nodes and change the ledger or the blockchain because you'd have to hash every single one of them. Okay, so decentralization and centralization. What's the difference? So in a centralized system, all units and all nodes are controlled by a single entity, and they're all under the same, they're all under the same domain in a sense. In that case, it's prone to a single point of failure, such as like if one server fails, it's handling the load of some like network traffic, then the system is compromised in a sense, or it's going to slow down significantly if it's not a sufficiently redundant system. It's also DDoS prone. Like let's say, yeah, the same thing. Let's say a bunch of botnets attack Facebook. Their systems aren't going to go down, but their services are going to be severely slowed down because since Facebook is centralized, it's not a decentralized social network. Also, centralized systems are easier to implement. It's really easy to host an app these days due to like AWS and all these DevOps services that are out there. So in terms of that, it's really easy to implement compared to decentralized systems and decentralized applications. There are frameworks out there that makes it easier to develop decentralized apps, but it's still much easier to develop like centralized services. They're also both horizontally scalable. So let's say Facebook adds some new hardware, or they add some like faster hardware or more expensive hardware, or if they add more servers. That's both examples of horizontal and vertical scalability, and centralized systems are generally faster. In decentralized systems, it kind of makes sense, right? Like, there's no single point of failure because there's no single entity controlling the network. It's distributed geographically, and its function is distributed as well. Multiple nodes host the network, and it makes it like highly redundant. However, they're prone to majority attacks or 51% attacks. Basically, what that is if you control the majority of the network, if one entity controls the majority of the network, then they have total control of forward progress in the network, so they can fork the network, change the consensus algorithm, or do whatever they want with whatever services that the network provides. It's also horizontally and vertically scalable. In some and think about Bitcoin. Bitcoin is only vertically scalable. It's not horizontally scalable because the more nodes that join Bitcoin, it doesn't get any faster really. I mean, even at this point, Bitcoin is the most it's the most prominent cryptocurrency out there, and the network is very large. But despite that, like it's still very slow due to its consensus algorithm. And the only way to get faster on Bitcoin is to scale vertically, is to add more hardware, and that's problematic in a way. It's not horizontally scalable. Good decentralized systems have to be both horizontally and vertically scalable. And they also have good consensus algorithms for forward progress. So in order for the network to work, consensus needs to be obtained amongst all the nodes, which um, you don't know how these nodes are going to behave. You need to somehow get them to behave like independent of where they are, who they are, and what they're associated with. And because of that, it's very complicated to implement decentralized systems. So it's complex implementation. That's probably the hardest part with blockchain compared to centralized systems. They have a complex implementation, and in order to highlight the complexity, you have to go over to the Byzantine generals problem. So what is this? All it is, it's an analogy that highlights the issues of decentralized systems. So let's say some goal, some arbitrary goal in mind. In this case, it's going to be two enemy castles that two generals must attack simultaneously, and there's some incentive for this arbitrary goal. In this case, it's large reserves of precious metals and resources, so some monetary gain. And the generals are separated by a large distance, and they must decide on how to confirm the exact time to mobilize their troops. So basically, there are nodes distributed across the world. And the only way for them to communicate is the use of messengers. So they send messages back and forth, deliver messages. It would be like just a packet or email or something. So here are the issues with this scheme here. The generals need to be sure of like a lot of different aspects of this attack. Like how do they know that the messengers aren't spies, or how do they know that their messengers are going to survive the journey? How do they know that how do they know that the messengers will be bought out, or if the other generals will be bought out? Because like, there's a huge monetary gain. There's a lot of gold and resources, probably a lot of food, a lot of wine and stuff. So they could be bought out. In that sense, what if the messengers are incompetent? Like let's say they fall off their horse, or they're traveling drunk, or they lose the message, or they just get attacked, or they get mauled to death by something, or let's say their horse just runs away. How do generals know that each message is authentic? Yeah. What if the messengers get kidnapped and they change the message, or if the messengers change the messages themselves because they're also spies? Who knows? Or how do the generals know that the other general and his army hasn't been annihilated yet? So yeah, like the same situation as what's it called? I don't know. Where was I going with this? Yeah, I don't know. How do the generals know that the other general and his army hasn't been annihilated? What was I gonna say for this? Um. Oh yeah. What if the castles mobilize their army and it attacks the other generals? Like you know, basically, are they there or not? Anyways, how do the generals know that the other general is also not a spy? So yeah, collusion. Like these are just all the questions that are brought about in the Byzantine generals problem, and it's analogous to decentralized systems. And here are just some bullet points to sort of like highlight the analogy. So unpredictable actors, so like the messengers and generals, they're both unpredictable. So they could be malicious, or they could be faulty or incompetent. You know, so how do you get around that problem? Message corruption. So like let's say the messenger loses the message, or they die, or they change it, or something happens to the message. How do we deal with that as well? Or timing. The whole problem is about timing. How can they attack the castles at the same time? You know, and the communication protocols for decentralized networks, they have something called windowing to make sure messages are sent at the right exact time, and it's just a whole timing synchronizing thing. A vetting process. So, um, I guess let's say that the messengers have to go through like years of training in order to become a messenger. That could be the vetting process for that in that case. And this is just an analogy for decentralized networks, whether they're permissioned or permissionless. And what does that mean? So Bitcoin is a permissionless network. All you need to do is have a sufficiently powerful enough mining rig in order to join the Bitcoin network. And that's it. And that's it's sort of cost prohibitive in a way. I guess you can debate that's not really permissionless because only rich people can do it, or people who have money can do it. But regardless, if you ignore the monetary part, it's permissionless in a sense. About permission networks? Well, you compare uh, Bitcoin's protocol, its consensus protocol, to Ripple's consensus protocols. Because in Ripple's in XRP, their network, it's permission in a way, and that might make you think it's centralized. Well, no, Ripple is still decentralized. It's just that in order to become a validator, you need to be sworn in a sense. Like Ripple's not gonna Ripple's not the only um, aspect in confirming whether or not you can join their network, because I'm pretty sure there's other I'm pretty sure other nodes in the UNL list have to confirm new nodes to join the network. Ripple's not the gatekeeper in that sense. So, and it's still decentralized despite the fact that Ripple is a decentralized, despite the fact that Ripple is a permission network. So yeah, permissionless is sort of a vetting process type of thing. All right, incentive structure. So what does that mean? So like, we need some kind of reward system that allows that motivates nodes to behave in a way that is good for the system and not malicious. And with an incentive structure, there's also like sort of a punishment structure. So if you behave maliciously or not within lines of the system, they'll probably take some funds away or remove some kind of like reputation, and it ties into like a reputation system. So the better you act, the more the protocol will promote your node for your services. And in Sia Coin, their Sia protocol, they do have a reputation system, or at least in their white paper, they stated there's a reputation system. So yeah, basically nodes in that network, if storage providers are doing great, the system will promote them more, and you know that's just the reputation system. So yeah, these are just this is just a list of all the issues with the Byzantine problem, and in this sense, good decentralized systems will be what's it called, fault tolerant to all the issues that are associated with decentralized systems. So all of these problems in the Byzantine general's problem, a fault tolerant decentralized network will handle at least most of these in under like most under usual circumstances. And you'll hear a lot the term Byzantine fault tolerant consensus algorithms. That's where this comes from. It's a reference to the Byzantine generals problem. So yeah. Anyways, now let's tie this into cryptocurrencies and its first use cases for blockchain. Like I mentioned before, blockchain was invented in the 1990s, and its first use was for time stamping. It was created by Stuart Haber and W. Scott Stornetta to digitally timestamp documents in order to make them tamper resistant. Now, this was all fine and dandy for the 1990s because computers weren't that powerful. But as computers got more powerful, time stamping documents became tamper prone because all you had to do is recalculate the hashes. So blockchain sort of fell out of use until decentralized systems became a thing, and Satoshi Nakamoto utilized those concepts in decentralized systems to utilize blockchain and create a payment network, and that's just Bitcoin. And this is like the pinnacle of all of these concepts is to create a decentralized payment system or digital money. And so cryptocurrencies. So what is it really? All it is, it's just account balances, coin supply, and prices that are tracked on an immutable distributed ledger. That's what a cryptocurrency is. And it's the crypto part is that it's all tied together, and all the security is enabled by cryptographic algorithms and hashing algorithms. So the ledger is secured by the blockchain, and I just demonstrated that the blockchain it has data integrity by design. So that's what the ledger is secured by, and it's updated by the consensus algorithms. So in order to get forward progress on the decentralized cryptocurrency network, a consensus algorithm must be utilized, and that allows the blockchain to be updated, more transactions to happen, so on and so forth. And accounts, so like account balances, there are, like I said, what a cryptocurrency is, all it is just a series of account balances and a way to keep track of money being moved between account balances. And those account balances are indicated by addresses generated by some cryptographic private key. Okay, so these accounts are associated. They're also associated to people. So multiple accounts can be owned by multiple people. And so what does it mean? So that's what it means to own a crypto token. And it's the same thing as a bank account. Like if you own money, you own an account that stores a number that represents dollars or euros or Japanese yen in some kind of digital account. And the same thing, the same type of thinking applies to blockchain and cryptocurrencies. So owning a crypto token, all it means is that you have access to an address or an account, like in other words, an account that has some balance. So it's a glorified number in a database. So you own an address that has some number that indicates how much crypto tokens you own and their associated value to fiat currencies. So, but like, how do you know that your balance is actually correct? Like, we don't really question the balance we have in our bank accounts because we sort of just assume the integrity of the bank, which is slowly like disintegrating because of like bank runs and like the whole financial crisis and stuff. So like, we don't really question banks when we actually should. But in this case, in cryptocurrencies, we don't really question the blockchain because we're told okay, this is inherently secure due to its design, and it can only be updated via consensus algorithms. Well, that's the thing. um, we don't question it because we know that the consensus algorithms and all this math and all this cryptocurrency stuff and all this cryptography stuff and hashing algorithms, the security of our money is guaranteed by mathematics. That's what we place our faith on. That's what we place our faith on. Our balance was previously confirmed by consensus algorithms. All of that, all the nodes, basically comparing their transactions and running their hashing algorithms to ensure that okay, your balance is supposed to be this amount, and we have confirmed this several times. So with the timestamps and hashings and all that stuff. So yeah, and so that's how the cryptocurrency system all comes together. That's how it all cohesively works as one functioning payment network. Consensus within decentralized networks in combination with blockchain's inherent integrity allows for the feasibility of cryptocurrencies. That's what I was getting at basically. All these subcomponents tie together to produce some functional payment system. All right. So that's basically my take on the whole blockchain technology stack. Now let's just go wrap this up. So we went over data structures in order to explain how blockchain is just a glorified data structure. It's a glorified linked list, but by design it is a secure. By design it ensures data integrity due to the linking of hashes. And I also explained how it's sort of useless unless the blockchain is distributed and decentralized in a system where no single person is able to change the ledger. So it's a decentralized it is a decentralized system that only operates under consensus between nodes that would normally not be in agreement with one another. The consensus algorithms is what makes the whole decentralization functional. And I went over decentralized system issues by highlighting the Byzantine generals problem, all those problems associated in that analogy highlight the problems with decentralization. And then we went over cryptocurrencies and the first use cases of blockchain and how blockchain was created in the 1990s for time stamping and eventually resurfaced for payment systems. And in the end, I explained how decentralization and consensus and the inherent data integrity provided by blockchain, all those pieces of technology tied together to allow for cryptocurrencies to exist. I also explained what it means to own a crypto token. I want to really highlight this because it seems sort of nebulous and it's really out there for most people to understand what it means to own a crypto token. So I'll just go over it again. Owning a crypto token means that you have access to an account or like an account address that has a balance of crypto tokens. So you can access an account that shows your balance, and your balance was previously confirmed by consensus algorithms. So you can be sure that this is your money because the consensus algorithms, all the cryptography, all the hashing confirmed it for you. And because we have consensus, decentralized networks are capable of providing these payment networks. So yeah, here we go. That is it. Hope you guys like this video. If you want to see more content like this or new ideas, please hit subscribe and like. Comment down below and of what you thought of this, and I'll see you soon. Thanks.